And I think we'll have two talks about Kitaev materials.
I actually somewhat changed my
Okay,
talk.
I forgot your title anyway.
After hearing all the great talks here, I decided to give a more diverse talk on quantum materials,
Okay,
because
good.
what I do, and that's what I do, and I thought people may be more interested in seeing a diversity of materials. Let me see if I can connect this. And in fact, before I start my talk, I would like to sincerely thank the organizers of this wonderful meeting, Jiadong, Liang, Shana, among other members of the organization committee. Thank you so much for doing such a great job. This meeting was so much fun. It went so smoothly. I think everybody agrees me on that, so thank you. So this was, as Jiadong mentioned, this was the original title of my talk, basically chemical and physical routes toward the Kitaev spin liquid materials. And then I thought to add a few other things to it so that the talk is a bit more flavorful. And I'm happy to, I won't go into too much details because there's too much here to cover. But I'm trying to giving you a broad talk, and I'm happy to discuss the details later. I start with acknowledgements from many national labs. My group is a quantum materials program. We have to go to national labs for the characterization of our samples. Also, academic collaborators. Some of them are here among you. So I'm very grateful to all of them for making this work possible. This is just to give kind of a broad perspective of my research program. We make bulk crystals of various compounds. We are after phenomena such as quantum spin liquid, polaronic systems, extreme magnetoresistance, topological superconductivity, chiral systems, van der Waals systems, flat band, and especially the first 2 days of this conference was overwhelmed by 2D materials, so I thought I have to add something 2D at least, so I'm not only 3D. I start with the quantum spin liquid systems. Particularly, the focus of research in my group is on Kitaev spin liquid materials. And the reason, there's also, I give you some publications related to each topic. The reason why I'm interested in the Kitaev spin liquid systems is because this is the only proposal for a spin liquid which is analytically solvable. And that's the very reason to believe that such a phase exists, and it's really worthwhile to work on such a phase. Although we have not yet been successful to identify an actual Kitaev spin liquid material, but there is good motivation to try it. I don't think if I need to introduce the model for this audience. It's basically a model on a honeycomb lattice with spin half particles that interact in a bond directional manner. Soon after this proposal, 2 iridium-based oxides were found to sort of satisfy the requirements of this model, lithium iridate and sodium iridate. They have been studied intensely in the past 2 decades. These systems, the combination of crystal electric field and spin orbit coupling provides an effective spin half on these systems. And there's plenty of experimental evidence for these materials to have, to be strongly frustrated and to show excitations that look like what you expect for a Kitaev spin liquid. However, both of these compounds ultimately order magnetically at around 15 Kelvin, and therefore eventually their ground state has a long-range order, and that's what you want to avoid in order to enter a spin liquid regime. Unfortunately, there's not a whole variety of these systems, and the contribution from my group was to devise a chemical pathway to make other types of these compounds, and I'm going to talk about that. But before that, I would like to also mention that the fact that these systems order magnetically tells us that their Hamiltonian is not governed by only the Kitaev term. There must be at least a Heisenberg term, and there could be other off-diagonal exchange interactions that drive the magnetic ordering and determine its texture. These different interactions in the Hamiltonian are controlled predominantly by the iridium-oxygen-iridium bond angle. And for a chemist, it would be interesting to tune that bond angle and basically tune the relative strength of different terms in the Hamiltonian. So for example, the Kitaev term is known to be a super exchange interaction, which obviously depends on the bond angle between d orbitals of iridium and p orbital of oxygen. The Heisenberg interaction is predominantly a direct exchange interaction, but that could also be tuned by tuning the spatial extension of the d orbitals. For example, if you go from 5D to 4D to 3D, you reduce the spatial extension of orbitals and you change this term. And the off-diagonal exchange interaction is a more complex term that depends on both of a combination of these two interactions. So our goal is to make more materials where we can tune the bond angles and therefore cover the so-called global phase diagram of Kitaev magnets. We do this by a technique called topochemical exchange reaction. The idea is that we start from the parent compounds, lithium iridate and sodium iridate. We take them as a structural platform. And then we perform exchange reactions. We exchange some of the alkali here with transition metals such as silver, copper, and hydrogen. And we make new versions of these compounds. Here's an example of it. Lithium iridate, if you remove the interlayer lithium atoms and replace them with silver, you make a new compound, silver lithium iridate. But when we do that, the important structural change in this reaction is that when you take the lithium atom out and you replace it with silver, the interlayer coordination chemistry changes. Lithium atoms are coordinated octahedrally, but silver atoms are coordinated in a dumbbell or a linear fashion. And when you change that, in order to make such a change of coordination, the oxygen atoms within the layers must move to accommodate for a change of this coordination. And as a result, you are in fact changing the iridium-oxygen-iridium bond angle within the layers by changing the atoms that goes between them. And of course, that would tune the different exchange interactions that depend sensitively on the bond angle. And that is our way of spanning this phase diagram by creating new topochemical versions of these compounds. So here I talk briefly about a few of these, the experiments we did. One of these materials is silver lithium iridate. This system, we synthesize it. We use TEM to sort of quantify the disorder in these materials. It took several years to kind of perfect the synthesis procedure, make sure there are no interatomic inter-site disorder in this compound. This is our tool to basically show that this material does not have such disorder. And then we perform experiments such as mu-SR. The oscillations in muon spin relaxation is a signature of long-range magnetic ordering. And those oscillations in this compound, silver lithium iridate, do not start until about 8 or 9 Kelvin. And that is the temperature for long-range ordering. This is also confirmed by NMR measurements where you see the drop in 1 over T1 at about 9 Kelvin. And this is a lower temperature for magnetic ordering than the parent compound of this compound, which is lithium iridate. So we could, in some sense, we could get the material closer to the south pole of this global phase diagram where a Kitaev spin liquid exists. So this is an example of such a reaction in a 5D system. But we also perform topochemical exchange reactions on 4D systems. And here is an example of that. This is lithium rhodate. We again exchange lithium atoms with silver atoms and change the bond angle between rhodium, oxygen, and rhodium atom this time. Now, this experiment was motivated, going from 5D to 4D was motivated by this sort of phase diagram that I made. Basically, this is a phase diagram of the ordering temperature of these Kitaev oxide materials as a function of their Curie-Weiss temperature, which is coming from magnetic susceptibility analysis, and it roughly quantifies the strength of magnetic interactions. The iridates all are on the negative side of this phase diagram, so they have antiferromagnetic exchange interactions of about 100 to 150 Kelvin strong. And when you exchange them, the TC basically goes down in this system. So that kind of goes, if you will, the right way, quote unquote. The ordering temperature is suppressed. But then there is this interesting material, lithium rhodate, which orders at about 6 Kelvin, also on the antiferromagnetic side. And the idea we had was to exchange this material and hopefully follow what happened in the iridates and maybe this time suppress the TC completely to 0. But unlike many of my good ideas, this went wrong. In fact, the lithium rhodate, after the exchange reaction, its TC went up by an order of magnitude. It went from a 6 Kelvin spin glass to 100 Kelvin robust antiferromagnet. So definitely it was not what I expected. But still, it was a very interesting phenomenon. And we spent some time understanding why this happened. Why did it go wrong? Or why did it go the opposite direction to what we thought? And in fact, what we found was that when you do this, when you perform such exchange reactions, you induce a trigonal distortion in these materials. The trigonal distortion is in each, if you take one octahedron, which is shown here, and you push the top and bottom triangles of the octahedron toward each other, you have a trigonal compression. If you, you can also have a trigonal expansion. In this case, we found out that we have a trigonal compression. Here, we basically characterize the trigonal compression via scattering measurements. We get the positions of oxygen atoms and the bond angles between oxygen, rhodium, and oxygen, and then we calculate a bond angle variance. And we found that in the parent compound, the bond angles variance is small, but in the exchange material, the silver exchange material, the bond angle variance is large. And that basically quantifies your, the amount of trigonal distortion. And then later, we also, with the help of my colleague at Boston College, Ing Ran, we basically looked into the change of the spin orbital wave function after you have this trigonal compression in the material. And we found that whereas in the lithium rhodate, your spin orbital wave functions have a cubic symmetry, after the exchange reaction, they have a trigonal symmetry because they are now made of a different linear combination of d orbitals, and therefore the trigonal compression changes the spin orbital wave function. In a way, by performing this chemistry, we change the fabric of the spin orbital wave function of the material, and that also changes the anisotropy of the system. This parent compound is a J-effective half, whereas the exchange compound is an Ising-like system. In fact, it's still spin half, but in an Ising regime. So that's what we did. This was a chemical pressure experiment, if you will. But now we had a high temperature, robust antiferromagnet with a honeycomb lattice and spin half, and then we decided to go the opposite way. We didn't give up on maybe realizing a spin liquid-like sort of state in this material. So we physically pressurized it, and we found something very interesting. We found that the TC of this material is suppressed from 100 Kelvin down with a pretty fast rate. It's among the fastest rates of TC suppression with pressure that I know of. And here is basically the raw data. You measure magnetic susceptibility. The peak is the nail temperature or the ordering temperature, and it goes down very clearly and visibly with increasing pressure. And so from these susceptibility data, we can extract the Curie-wise temperature and the ordering temperature. Both of them are going down. But we can also extract the effective moment, and that does not change. And this is a really important finding, because in many honeycomb Kitaev materials, when you pressurize them, the honeycomb structure distorts. It dimerizes. And therefore, you no longer have a honeycomb lattice. And you lose magnetization, but it's not because you're tuning the relative strength of, let's say, Kitaev to Heisenberg interaction. You lose magnetization because you lose the magnetic moment altogether due to that dimerization. What is beautiful in this material is that it's the only honeycomb Kitaev system that survives a dimerization at pressures more than 2 GPa. The other systems dimerize before this pressure very quickly, actually. And now here is again, so we show what happens to magnetic ordering at high pressure. So this peak exists and it goes down with increasing pressure, but at some point we just lose this antiferromagnetic peak altogether. So the order goes away, the system is not structurally dimerized. So this is a very kind of exciting material, in fact. Here is a diamond anvil cell measurement, X-ray measurement in diamond anvil cell. We looked at the evolution of Bragg peaks with increasing pressure. Indeed, at some 6 GPa, there is a dimerization transition, but your antiferromagnetic order is gone by that pressure. And that's really the key finding, that this system dimerizes eventually, but at much higher pressure than when you're suppressing its antiferromagnetic ordering. And so here is a phase diagram of silver lithium rhodate. The work is under review. We hope it gets published soon. And so basically, there is a window here between the suppression of magnetic ordering and the onset of the structural transition, and interesting thing can happen in that window. And so, of course, we interpreted this work in terms of the tuning of Kitaev to Heisenberg coupling by tuning the bond angle. OK, so that was one system. Now, I would like to talk about maybe another system, this time about a chiral material that shows very strong electron-phonon coupling. Typically, we think of phonons as basically scatterers of electrons. So conduction of metals becomes poorer as the electrons scatter off of phonons. But there is a regime where phonons can exchange momentum with electrons without losing much of that momentum into anharmonic processes. And in that regime, which is also known as phonon drag, in fact, the interaction between electron and phonon can lead to an enhancement of conductivity. And we're interested in these materials for various reasons. One of them is that we are just looking to design metallic systems with extremely high conductivity so that maybe we can reach a limit of hydrodynamic transport of electrons. So that's sort of the motivation. We made 4 compounds, niobium silicon 2, niobium germanium 2, tantalum silicon 2, tantalum germanium 2. And in these systems, we looked at the evolution of mobility, but particularly 2 types of mobility, the transport mobility and the quantum mobility. The transport mobility comes from transport measurements of resistivity and Hall effect, as we've seen, in fact, in our previous presentation. The quantum mobility comes from quantum oscillation, which also, thankfully, our previous presenter gave us some introduction to those experiments as well. Now, here is the crystal of niobium germanium 2, the first compound, which is the most interesting one. It's a chiral crystal. The resistivity measurements, the residual resistivity goes down to nano-ohm centimeters, in fact. And it also shows a peak in the Seebeck, in the temperature dependence of Seebeck coefficient, which is an evidence of electron-phonon coupling or a phonon drag regime. Now, we measure in these systems, we measure the Hall effect, or rho xy, and the resistivity rho xx. And these systems are not single band, so you cannot just divide the Hall coefficient by resistivity to get mobility. For these systems, you have to fit both resistivity and Hall effect to these multi-band expressions, and you have to do simultaneous fits so that you can get reliable measures of mobility and carrier concentration. So we get those. So that's how we get the transport mobility. And then we perform quantum oscillation experiments at high fields. And from an analysis of those quantum oscillations, we get the quantum mobility. Basically, what you need to do is to look at the damping of quantum oscillations with field. And from that, you get something called a Dingle temperature, which gives you relaxation time. And then you need the effective mass to get the quantum mobility. And that you get from the temperature dependence of quantum oscillation via an analysis called Lifshitz-Kossovich analysis. So that's how the experiments are done. This is my student Xiaohong Yao. So we basically go to MagLab. We are users of this facility. And so basically that's how we perform the quantum oscillation experiments. Now, we saw a very strong, a very large mobility, especially in niobium germanium 2. And we saw that the transport mobility in niobium germanium 2 is much larger than the quantum mobility. And this ratio is actually tuned across this series. When we go to tantalum silicon 2, in fact, the quantum mobility is larger than the transport mobility. And so we wanted to see how, what is the sort of electron-phonon interaction in these systems and how that changes. So for that, I collaborated with my colleague next door, Ken Birch. He measured the Raman spectra in these systems, and we looked at the temperature evolution of Raman peaks. And we found that there is a fundamental difference between that temperature dependence of Raman peaks between the silicides and the germanides. For the silicides, as we increase the temperature, the Raman peak line peak increases. Basically, the Raman peaks become broader. That's what you expect from a system that has anharmonic phonon interaction. So phonons basically anharmonically decay into each other, and that follows a Bose statistics. Phonons are bosons. This is called the Clemens model. This is the complete normal expectation of from phonons. What's exciting and interesting and not expected is what happened in the germanides that have such high transport mobilities. In these systems, when you measure the line width of phonons, it initially increases, just like the silicide, but at some temperature, it actually decreases, which is not at all what you expect from a phonon statistics. In fact, the temperature dependence of these phonon line shapes follows a Fermi function instead of following a Bose function. And that means that there must be a strong coupling between phonons and electrons, in the sense that phonons are kind of obeying almost the behavior of electrons that are fermions. And we showed that, in fact, this is it's not only limited to this series of niobium ditetrolite or tantalum ditetrolite systems, but we also found the same behavior in other on topological semimetals. In fact, the high conductivity of some of these topological semimetals has been attributed largely to topological properties, but we believe that the phonon-electron interaction could be another way of explaining such high transport mobilities. Yeah, so basically I stop on this topic and I go to the next one. Do I have time, Jedong?
Yeah, 5 minutes.
Okay, good. So I'll try to be quick. I briefly tell you our adventures in 2D materials. Really, the first 2 days of this workshop made me change my talk. I said, I have to say something about 2D materials. So we have made the following contribution to 2D materials. Of course, you all know about chromium iodide, and we had a workshop yesterday and many interesting talks in the past 2 days about this system and related compounds. But all I want to say is that chromium iodide is not a single sort of system in this structure. There's actually chromium bromide and there is chromium chloride. And what we found is a chemical pathway to mix these things and make heteroanionic 2D materials. And that's a very, that is, of course, from a chemistry perspective, it's interesting. But from a physics perspective, it's also very interesting for the following reason. So here I'm showing a series of crystals where we start from chromium chloride, we go to chromium bromide. This one is pink, this one is green, and the compositions in between change color. So when they change color, that means that the optical gap is being tuned as you tune the composition. And that can be understood from a molecular orbital perspective, because we are basically mixing chlorine with bromine in the octahedral cage. And as you do that, the sort of the ligand orbitals, the energy of the ligand orbitals changes, and that changes the optical transitions, basically. And the other thing that happens that's very interesting, other than tuning the optical or the band gap, is that we also tune the magnetic anisotropy. So this is chromium chloride, magnetization measured with field in the plane and out of plane, and you see that the in plane is the easy access. But as we increase bromine, the red and blue curves cross. You see that now here the red curve saturates before the blue curve, here the blue curve saturates before the red curve. So in fact, the anisotropy goes from in plane to out of plane continuously by tuning the composition of your non-magnetic elements, not the magnetic element. And that is, I think, a very interesting chemical pathway to tune van der Waals system by tuning the non-magnetic ligand, in fact, because the spin-orbit coupling of ligand actually determines the anisotropy in these systems. We also showed that the TC can be tuned linearly, Curie-Weiss temperature is tuned linearly, the interlayer separation tunes linearly, the optical gap is tuned linearly. So. And then we went to kind of sort of a combination of 3 halides, this time chlorine, bromine, and iodide. And here we made triangular phase diagrams of the Weiss temperature and TC. And by dividing these two by each other, we found a triangular phase diagram of the frustration index. And we found that, in fact, somewhere in this phase diagram between chromium chlorine and bromine, specifically this red region, you have a much stronger magnetic frustration than the rest of this phase diagram. And there are some discussions about chromium iodide being possibly a kind of a Kitaev candidate because it has a honeycomb lattice and spin 3/2. But actually, my group is showing that you should not look at this side of the phase diagram. You should look at the other side of this phase diagram. And again, a quick interpretation of this is that when you change the spin, when you enhance the spin-orbit coupling of the ligand, the magnetocrystalline anisotropy goes toward off-plane, which is the blue region, whereas if you increase the spin-orbit coupling of the transition metal in a DFT code, then the magnetocrystalline anisotropy goes in plane. But in compositions between two, you have a white line where these two anisotropies are compensated, and we believe that's what happens in this red region. It's between chlorine and bromine with a specific concentration. I knew that I may not have enough time, so I want to thank my group. These are the students who did all the work, and funding agencies, and of course, the organizers of this workshop. But I do have a couple of more slides if you want me. If I have a few minutes, like 1 or 2 minutes, I can show one more thing. Jiadong, is that okay? Is that allowed?
Yeah.
Thank you. Well, okay, at least I was prepared to finish it on that note. Good. So the last thing I want to show you is a little bit of interesting observations on polaron materials. So we are working on a few intermetallic compounds that are magnetic semiconductors, really, but I mean, they look like more like a bad metal. So let me explain what these things are. And they show very interesting physics. So here I'm showing, this is europium cadmium to phosphorus 2. This is the first system that we studied. I'm showing resistivity as a function of temperature. At zero field, which is the black data, this system shows a very large peak in its resistivity. Now, if you look at the temperature dependence of its resistivity from room temperature down to low temperature and just zoomed into this in this region, because that peak is so large that you have to zoom in this region, you basically see that the resistivity goes down in a metallic way with decreasing temperature, but the actual values of resistivity are giant. They're of the orders of, this is 24 milliohm centimeters. This is well above the Mott limit. So this system must be an insulator with these resistivities. But it still acts as metallic in a sense. So that's why I call it a bad metal in analogy with correlated systems. Now, this system shows a gigantic peak in its resistivity. Then you apply a tiny field of 0.2 Tesla, and that peak drops by more than a factor 2. And when you go to about 5 Tesla, it drops by more than a factor of 20. And if you look at this negative magnetoresistance, it reaches 10 to the 3%, which is larger than colossal magnetoresistance in single crystals of all manganites. And now this system, interestingly, so colossal magnetoresistance is actually a very well-known phenomenon. During 90s and 80s and 90s, everybody studied them. But this phenomenon was understood in terms of double exchange interactions and Jahn-Teller distortions in correlated oxide materials. This system does not have mixed valency or double exchange interactions. It does not have Jahn-Teller distortions. Here is an X-ray data, shows that this does not go through any kind of structural distortion across its ordering temperature. It is not even an oxide. It's a phosphide. And yet, it shows a colossal magnetoresistance that beats all the manganites. And so that's very interesting to understand where that thing comes from. And our current understanding, which is very poor, is that this system, in fact, orders at about 11 Kelvin. That's the blue region in that phase, in this resistivity zoom plot. It's a narrow region because it just happens between 11 Kelvin. But this giant peak in resistivity happens between Tn and about 5 times Tn. And so it's happening in the regime of magnetic fluctuations, not in the regime of magnetic ordering. So this effect, whatever it is, it seems to be related to strong magnetic fluctuations. But those fluctuations could be coherent. They could be, for example, polaronic fluctuations. One of my colleagues, Benedetta Flebus at Boston College, has another theory that this could be topological Meron, anti-Meron type fluctuations that can be suppressed sensitively with a magnetic field, and that's why this peak drops. There are competing scenarios, and as I said, I'm not going to have much time to go through it. But there's one other thing I want to add to it. We made different versions of this system. We made phosphorus, arsenic, and antimony. And the reason why we made those versions is because this system is a layered antiferromagnet, and the layers are connected via this pnictide, arsenic, phosphorus, or antimony. So we thought that by reducing by increasing the size of the pnictide, we can enhance the interlayer coupling, because these orbitals are becoming larger, the p orbitals basically, and there is more coupling between the layers. And indeed, as that happens, Tc goes down, which means that fluctuations become stronger, and this peak becomes suppressed. The black data is the phosphide system, where the peak is giant. The arsenic system has a tiny peak. The antimony system has maybe a blip. And so it basically shows that as we make the electronic structure more 3D, this effect goes away. And so it's another kind of way of interpreting this in terms of fluctuations of some sort. In the beginning of my talk, I showed a picture of Boston College in the fall. I think you all have seen the picture of New Hampshire in the fall, which is really, really perhaps the most beautiful scenery. Again, huge thank to the organizers of this meeting, and thank you for being patient and staying until end of this meeting. Thanks.
Thank you so much, especially the last slide. Okay.
I think I have two quick questions. So in the last set of materials, do you have any idea what the magnetic susceptibility looks like as a function of temperature?
Yes, so the magnetic susceptibility, I don't have the figures here. This is published work. Basically, it looks like this is an A-type antiferromagnet. So when you measure it with the field in the plane, you see a peak like an antiferromagnet. When you measure it, in the plane, you see like a ferromagnetic transition. Out of plane, you see like a peak like an antiferromagnet. So spins basically alternate like this.
Like Curie-Weiss-like?
It is Curie-Weiss-like. It is, yes. So it's actually fairly localized, in fact. Yes.
Okay. And then my other question is about the phonons. So I forget which material showed this anomalous behavior.
The germanium, yeah.
The germanium, yeah. Do you have any complementary investigations of the lattice? Like, do you notice any anomalies, maybe like a negative?
No, in fact, that's a
just
very
normal?
interesting, I think, neutron scattering experiment, and I'm happy to discuss. If there could be, this is a chiral crystal, there could be very interesting dispersion of phonons, for example. We only got Raman, and Raman only sees the optical phonons.
Even if you look at the temperature dependence of lattice parameters, or
Yeah, temperature, well, what we have done, we've done crystallography at high temperature and low temperature, not at thorough temperature dependence. There is no structural transitions, there's nothing dramatic. But I think what's interesting in these systems is to access the acoustic phonons, ultimately, which neutron could do.
Yes, so related to this material,
Yes.
so why there is maron, anti-maron? It's a triangle lattice, so we don't expect this kind of.
It is
It's
in
a
a
triangle lattice, right?
Well, that's right. So the maron antimaron that I told you about is not exactly in this system. So my colleague formulated a toy model for a square lattice.
Okay.
And so she basically showed that this is a toy model, that such a thing can happen.
So I guess opposite to what you see for this last set of materials,
Yeah.
for the iridates, do you see them become more two-dimensional when you add the silver? 'Cause you should be spreading out the...
Oh, that's a good question. So in the silver, in those systems, when we go from, for example, lithium to silver, it actually becomes more metallic. However, I can explain that in the sense that when you go from lithium to silver, silver is, of course, a lot more, it makes a lot more covalent bonds with oxygens. And so it's a larger atom. So it increases interlayer separation, and one can say the system can become more 2D in that sense. But if you look at the electronic structure, you'll see that there is some finite covalent bonding between silver and electron, and that actually prevents you from going to 2D. That's a good chemistry question, actually. Thank you.
I presume your europium is divalent.
It is divalent, yes, you're right. And we also looked at the X-ray absorption to see if there is any mixed valence, and we didn't find any. Also, when you measure magnetization as a function of field, the saturated magnetization goes exactly to 7 Bohr magneton, which correspond to spin 7.5. This is the very relevant and important question.
Okay, so last question. So in one of the slides, there is the baby. Is it your 4 months baby?
No, actually my baby is 5 months old, and that is not my baby. But it's just the expression in that, now I see everything in terms of babies. So yes, the expression was wonderful.
And
Of
thank
course.
you.
Thank you very much.